Picture it first, before anything else. 600 million miles from the sun, in the outer dark where sunlight arrives as little more than a bright star among other stars. A moon the size of Britain is erupting. Not metaphorically, not geologically, in the slow-motion sense that word usually carries. Erupting continuously, right now, as you read this, shooting jets of water vapor and organic molecules and molecular hydrogen from its south pole into space at nearly 1,000 miles an hour. The material rises in plumes that tower hundreds of kilometers above the surface, and some of it falls back as the purest water ice snow in the solar system, coating the moon in itself, making it the brightest object in the solar system after the sun. The rest escapes into orbit around Saturn and becomes part of its E-ring, a vast, diffuse halo of tiny ice particles orbiting a gas giant, sourced continuously from the interior of a moon that, by every model available before 2005, should have been cold and dead. That is what is actually happening out there, not in theory, not as inference. The plume is real. It has been photographed. Its chemistry has been measured. Its heat signature has been mapped. For 13 years, a spacecraft called Cassini flew through it, sampled it, and sent the data back to Earth, where hundreds of scientists have spent years working out what it means. And what it means according to the phrase that travels, the phrase that shows up in documentaries and headlines and funding proposals and the opening paragraphs of astrobiology papers, is that Enceladus has the building blocks of life. That phrase has been doing an enormous amount of work for 20 years. This is the story of what it is doing, how it got there, and what the evidence actually says when you press on it carefully, not to dismiss it, but because what the evidence actually says, stripped of the framing borrowed from a conclusion the instruments cannot yet confirm, is more strange and more interesting and more honest than the phrase the account settled on. The question is not whether Enceladus is remarkable. It is. The question is whether the account of why it is remarkable has been telling you where the evidence actually stands, or telling you where it hopes the evidence is going. Those are different positions. The difference matters. The plume was discovered by accident. That fact appears in the opening paragraph of almost every article about Enceladus, and then the account moves past it. One sentence acknowledging that Cassini was not looking for this, that the erupting jets were not predicted, not anticipated, not part of the mission's original design, and then straight on to what was found. The accident gets one sentence. What the accident produced gets everything else. That asymmetry deserves more than it receives, because the accident is not just a charming detail about how science sometimes works. It is a structural fact about every measurement that followed. Cassini's instruments were not built to find what they eventually found. They were built in the early 1990s, designed and calibrated against what scientists in that period understood about the outer solar system, which did not include the possibility of an active, erupting, chemically complex ocean world, hiding inside a moon that had previously been considered geologically dead. The instruments were extraordinary for what they were designed to do, but they were not designed for this, and that gap between what the instruments were built to find and what they were suddenly being asked to characterize runs through every number in the accepted account like a fault line that the account never fully stops to examine. Here is why that matters specifically. When a measurement is reported, what gets reported is not raw data. What gets reported is an interpretation of data produced by instruments whose sensitivity, range, and detection thresholds were determined before the thing being measured was known to exist. Every number Cassini returned from the plume carries within it the shape of the instrument that produced it. The instrument's limits become the measurement's limits. What the instrument could not detect does not appear in the data as an absence. It simply does not appear. And in an account that needs numbers, that needs to say what is present, and in what quantities the things the instrument could not see, are handled the same way the accident of discovery is handled. Acknowledged briefly, if at all, and then moved past. What was found, in the version most people have encountered, is this: water, complex organic molecules, molecular hydrogen, silica particles suggesting hydrothermal activity on the ocean floor, carbon dioxide, methane, and the phrase that travels with all of it, the phrase that does most of the work of making this feel significant: the building blocks of life. Press on that phrase before going any further, not because it is wrong, because it is doing something that language sometimes does. When it arrives too quickly, it is closing a question by appearing to open one. The building blocks of life sounds like a finding. It sounds like something Cassini detected and measured and returned to Earth in numbers. But it is not a finding. It is a frame. It is a way of organizing what was found that presupposes a particular answer to the question the framing pretends to leave open. Here is what that means specifically. The molecules Cassini detected in the plume, the organics, the hydrogen, the silica, are real. Their detection is not in question, but calling them building blocks of life requires a prior commitment to a particular model of how life begins, what conditions it requires, and what the presence of these specific molecules in these specific ratios actually implies about whether life exists or could exist in the ocean below. That model is not the only model. It is the one that was available and accepted and built into the framework within which the data was interpreted. And when a framework is doing the interpreting, the data will tend to look like evidence for the framework, not because anyone is being dishonest, because that is what frameworks do. The history of astrobiology, which is itself a young discipline, formally organized only in the late 1990s, given institutional form at NASA only a few years before Cassini reached Saturn, is largely a history of arguing about frameworks, about what life requires, about whether the requirements inferred from the one example of life we have access to are necessary requirements or merely the specific solution evolution arrived at on this particular planet. The field has not resolved this, it is still arguing. And that ongoing argument is largely invisible in the popular account of Enceladus, which presents the building blocks of life as if the question of what life requires had been settled, and as if Cassini had found the settled answer confirmed in the spray of a moon 600 million miles from the sun. It had not. What Cassini found was consistent with the conditions that produced life on Earth. That is a real finding. It is a meaningful finding. But consistent with is not the same as evidence for. And the distance between those two phrases is exactly the distance the account collapses when it reaches for the phrase that will travel. Enceladus was not unexamined before Cassini arrived. Voyager 2 passed within 87,000 kilometers of it in 1981 and returned images that showed a surface geologists described as unusually smooth, unusually bright, possibly young. The smoothness was noted. The brightness was noted. The youth of the surface was noted. And then the account moved on, because the instruments Voyager carried returned nothing that suggested what was underneath, and the framework available in 1981 did not include the possibility of a small, cold, distant moon harboring a liquid ocean driven by tidal heating from Saturn's gravitational pull. The framework did not include it, because the math at the time suggested it was unlikely. The tidal heating models available in the early 1980s predicted that a moon the size of Enceladus, at its distance from Saturn, in its particular orbital resonance with the neighboring moon Dione, should not generate enough internal heat to maintain liquid water. The numbers did not support it. And when numbers do not support a possibility, the possibility tends not to be considered, which is the correct scientific response. Given that you cannot design instruments to detect everything simultaneously, and you have to make choices about what to look for, based on what the available models suggest is worth looking for. But there is something inside that correct response worth examining. The models were wrong, not slightly wrong. Wrong in a way that meant an entire class of ocean world's small icy moons with subsurface liquid water maintained by tidal heating was essentially invisible to the scientific framework evaluating them. Enceladus fell below the threshold. The models said it should be cold and dead, and so it was treated as cold and dead. And when Voyager's images showed something anomalous, the smoothness, the brightness, the anomaly was filed as interesting and unexplained, and not pursued with the urgency it might have received if the framework had been different. This is not a failure of individual scientists. It is how frameworks operate. A framework is not a conspiracy. It is a set of working assumptions that allows science to proceed, that allows people to decide what to look for, what instruments to build, what missions to propose. Without frameworks, nothing gets done. The problem is not that frameworks exist. The problem is what happens to anomalies that the framework cannot explain. Sometimes those anomalies wait 20 years for the next spacecraft. Enceladus waited 24 years between Voyager and Cassini. In those 24 years, the anomaly of its smooth surface sat in the literature, cited occasionally, not resolved. When Cassini's magnetometer detected an anomaly near Enceladus in early 2005, a disturbance in Saturn's magnetic field suggesting something was releasing gas, the discovery was genuinely unexpected by the scientists running the mission. The accounts of that discovery in the papers, in retrospective interviews, in documentary segments emphasize the excitement. And the excitement was real. But there is something else in those accounts that does not travel as well. A recurring note of disorientation, of scientists reaching for frameworks that did not quite fit, of people trying to describe what the instruments were showing using language built for a different kind of finding. Carolyn Porco, who led the imaging science team on Cassini, described the moment of realizing what the South Polar images were showing as genuinely disorienting, not in the sense of being overwhelmed by wonder, though that was present too, but in the sense of needing to rebuild the interpretive context in real time. The images showed jets, active jets, material erupting from a small, supposedly dead moon in the outer solar system. Every prior framework for what such a moon should look like said this was not possible, and the instruments returning the data were not designed for this. They were designed for a different Enceladus, the Enceladus the models had predicted. What happened next is the part of the account that tends to be compressed. Between the detection of the anomaly and the press conference announcing the discovery of the plume and the subsurface ocean, a significant amount of interpretive work was done. Data was processed. Models were revised. Existing frameworks were stretched to accommodate what the instruments were showing, and language was chosen carefully by scientists who understood the stakes, but also quickly, because the discovery was extraordinary and the pressure to communicate it was immediate, and the vocabulary for describing an erupting ocean world on a moon of Saturn in accessible terms was being assembled in real time. The phrase that emerged, building blocks of life, was not chosen arbitrarily. It was chosen because it was accurate, in the limited sense that the molecules Cassini detected do appear in the chemistry of life as we understand it. But it was also chosen because it had already been used in the context of meteorite studies, of interstellar chemistry, of the early Earth, and importing it to Enceladus placed the moon inside a familiar story. The story of life's origin, the story of a universe that perhaps is not as empty as it looks. That story is compelling. It may be true, but it arrived before the evidence for it did. There is a scientist named Hunter Waite who has spent more of his career thinking about the Enceladus plume than almost anyone alive. Waite led the ion and neutral mass spectrometer team at the Southwest Research Institute, the instrument that returned the hydrogen data, the organic data, the numbers that became the building blocks of life. He is not a peripheral figure in this account.
He is one of the people most responsible for what we know, and for the careful, technically demanding work of turning raw instrument output into published findings. He also occupied a position that almost no one in the history of this question has occupied, the position of knowing, in precise technical detail, what the instruments actually measured, and also being asked repeatedly by journalists and documentary producers and NASA communications staff to translate that knowledge into language that a general audience would find compelling.
He did both things simultaneously, for years. If you read his public statements carefully, across the decade following Cassini's plume flybys, you can watch someone navigating the gap between those two languages in real time. In some interviews, he is precise: the data are consistent with a hydrothermal system that could support life. But we have not detected life, and the instruments were not designed to detect life. In other interviews, shorter ones recorded closer to press release dates, he says things like, Enceladus has the ingredients. The language shifts, not randomly. It shifts in the direction that serves the moment the interview is serving. That shift is not dishonesty. It is the normal consequence of occupying a position at the boundary between technical knowledge and public communication, in a field where the central question, are we alone, is one that generates a specific kind of public hunger that the precise language does not feed. The careful version, consistent with, could support, not designed to detect, is technically accurate. It is also, for the purposes of an account that needs to travel, too slow. It requires the listener to hold multiple conditions simultaneously to understand what an instrument limitation means for a quantitative finding, to resist the pull of the more dramatic conclusion. The careful version withholds the conclusion that the dramatic version delivers, and the conclusion is what the listener came for. So the account that travels is the one that delivers the conclusion. And the conclusion that travels is building blocks of life. What was lost when that became the account is not a technicality, it is the actual state of the question. The plume chemistry Cassini measured is consistent with three different explanations that are not equally interesting, but that the data cannot currently distinguish between. The first explanation is that the ocean beneath Enceladus's ice is a geochemically active environment where hydrothermal venting drives chemistry similar to what occurs at Earth's mid-ocean, ridges rich in the molecules that life on Earth uses. Energetically favorable for the reactions life on Earth runs, but entirely abiotic. No life. Chemistry that looks like life's prerequisite but has not become life, and may never become life, because the presence of the ingredients does not entail the presence of the process. The second explanation is that the ocean is abiotic, and has been so since Enceladus formed, that what Cassini measured reflects the initial chemistry of the solar nebula, preserved in a cold icy body and partially volatilized by the same tidal heating that keeps the ocean liquid. In this explanation, the organics are not generated by hydrothermal chemistry. They are primordial. Remnants, not building blocks in any active sense. The third explanation is the one the account has chosen, that the ocean is biologically active, that the chemistry Cassini detected is not merely consistent with life, but is, at least in part, produced by life by microorganisms living at the interface between the ocean water and the hydrothermal vents, doing what methanogens do on Earth, converting hydrogen and carbon dioxide into methane and water, and the isotopic signatures that, if they could be measured precisely enough, would distinguish biotic from abiotic chemistry. The account has chosen the third explanation not because the data supports it over the first two. It has chosen it because it is the most interesting, because it is the one that, if true, is the most important finding in the history of science, and because the data, while not supporting it specifically, does not rule it out. But not ruling something out is not the same as supporting it, and the accepted account has been living in that gap for 20 years. Here is a specific number that sits at the center of this problem. In 2017, a paper in Science announced that Cassini had detected molecular hydrogen in the Enceladus plume in concentrations suggesting active hydrothermal venting on the ocean floor. The hydrogen concentration was reported as between 0.4 and 1.4% by volume. The paper's authors were careful. They described this as consistent with hydrothermal activity, consistent with the conditions that could support methanogenic microbes, consistent with what you would expect if something like life were present. They were not claiming life. They were building the case that the conditions for life appeared to exist. The press release that accompanied that paper was less careful. Not dishonestly less careful, but the hedging in the paper, the consistent withs, the could supports compressed in translation into something that read more like a finding than a condition. Molecular hydrogen was presented as evidence that Enceladus has the energy source that life would need, which it is, but the distance between has an energy source life could use, and has life is the entire distance of the question. And in the press release, that distance shrank. Now look at the number itself, between 0.4 and 1.4% by volume. Who produced it and how? Cassini's ion and neutral mass spectrometer, the IMS, made the measurement. The IMS was designed to measure the composition of neutral gas and plasma in Saturn's magnetosphere. It was not designed to fly through an erupting plume from an ocean world and return quantitative compositional data about that plume's chemistry. When Cassini made its closest plume flyby in 2015, passing through at a distance of only 49 kilometers from the surface, at a speed of roughly 8 kilometers per second, the IMS was sampling material at a rate and under conditions that required significant modeling to interpret. The spacecraft was moving too fast for direct quantitative analysis of complex molecules. Some compounds decompose before they can be detected. Others are produced by the detection process itself, artifacts of the ionization methods the instrument uses. The team that operated the IMS spent years developing models to correct for these effects, to reconstruct what was actually in the plume from what the instrument returned. Those models are good. They are the best available. But they are models. And the numbers they produce, including the 0.4 to 1.4% hydrogen concentration, are model outputs, not direct measurements. That is not disqualifying. That is how planetary science works. Almost every number returned by a spacecraft instrument is a model output of some kind. The question is how the uncertainty in the model propagates into the number, and how the number is then used in the account that builds on it. In the case of the Enceladus hydrogen measurement, the uncertainty is present in the paper, acknowledged, quantified to the extent possible, handled responsibly by the scientists who produced it, and then largely invisible in the account that number enters when it leaves the paper and becomes the building blocks of life. The uncertainty does not travel. The number does. And a number without its uncertainty is not the same thing as the number with it. It is a different object. It supports different conclusions. When that number is used to say that Enceladus has what life needs, the uncertainty surrounding it, the uncertainty the scientists who produced it carefully documented, is exactly the uncertainty that determines how strong that statement actually is. There is a word for what is happening here in the philosophy of science. The word is underdetermination. It means that a given set of data is consistent with more than one theoretical explanation, and that the data alone cannot determine which explanation is correct. Underdetermination is not a pathology. It is a normal feature of scientific inquiry at the frontier. The question is not whether it exists, but how the account handles it. The Enceladus account handles it by not naming it. The papers name it. The careful papers by weight. By Chris McKay at NASA Ames, by Jonathan Lunine. By the people who have spent careers on this question, acknowledge explicitly that the data cannot distinguish between the abiotic and biotic cases, that a more capable mission is required, that the current state of knowledge supports the conclusion that the conditions for life may exist, but not the conclusion that life does exist. Those acknowledgements are in the literature. They are not hidden. They are simply not in the account that travels. And the account that travels has produced a specific distortion. If you ask most people who have followed the Enceladus story what Cassini found, they will say, evidence of conditions that could support life. If you ask them whether there might be life there now, they will say, probably, or possibly, or scientists think it's likely. That is not what the data shows. The data shows that the conditions for a particular type of life might exist. It does not show that life probably exists. It shows that it is not ruled out. Not ruled out is not probably. And the account has been running on probably for 20 years. There is a prior question underneath all of this that the account skips almost entirely, not accidentally. It skips it because answering honestly would slow the story down at the moment the story most wants to accelerate. The prior question is this: what does it actually mean for life to begin? Not what conditions does life require once it exists. What has to happen chemically, physically, in what sequence, over what time scale, under what constraints for the transition from chemistry to biology to occur? For the first self-replicating molecule to appear in a solution of organic compounds and begin doing what life does, which is make copies of itself that are slightly imperfect and therefore subject to selection? That question has been studied seriously for nearly a century. It has not been answered. This is not a fringe position. This is the consensus position of origin of life research, one of the most technically demanding and least publicly visible fields in all of science. The field knows an enormous amount about the chemistry that preceded life on Earth, about the molecules that were present, the energy sources that were available, the geochemical environments that may have supported the first steps. But the transition itself, the specific moment or sequence of moments at which chemistry became biology, remains genuinely, fundamentally open in ways that matter for what it means to say that Enceladus has the building blocks of life. Because building blocks implies a path. It implies that what comes next is assembly, that given the right ingredients and the right conditions, life follows. And that implication is doing enormous work in the Enceladus account without ever being examined. The path from organic chemistry to biology is not understood. The specific sequence of events that allows a collection of molecules to begin self-replicating in a way that is heritable and therefore subject to natural selection has been partially reconstructed in laboratory settings, under conditions that are contested, using starting materials that are debated, producing results that do not clearly generalize to environments like the one Enceladus appears to offer. The Urna world hypothesis, the most widely accepted current model for how the first self-replicating molecules might have formed, requires a specific set of conditions whose applicability to a deep subsurface ocean on an icy moon 600 million miles from the Sun is genuinely unclear. The accepted account of Enceladus treats the origin of life as a solved problem whose solution just needs to be applied to a new location. It treats the building blocks as sufficient or nearly sufficient evidence that the process will or might follow. But if the origin of life is not a solved problem, finding the building blocks does not tell you that you are on the path. It tells you that some of the chemistry is present. The path itself remains unknown, and there is something more uncomfortable underneath that. If the path from chemistry to biology is not understood on Earth for the one example of life we have access to, in the environment where it is known to have occurred, With the full resources of modern biochemistry available to study it then, the prior probability that life has arisen independently on Enceladus is not something that can be calculated, not approximately, not even in order of magnitude. The honest answer to the question of how likely it is that life exists in Enceladus's ocean is that we do not have enough information to form a probability estimate that is not essentially arbitrary. This is not the answer the account gives. The account gives something that sounds like a probability, something in the range of plausible to likely, depending on who is speaking and for what purpose. But those estimates are not derived from the origin of life being understood. They are derived from a prior distribution over how common life is in the universe, which is itself derived from having exactly one data point, which is Earth, which is not a basis for a statistical distribution in any meaningful sense. David Grinspoon at the Planetary Science Institute has pressed hardest on this in the literature, not as a fringe argument, as a mainstream concern within the field. Grinspoon has spent years arguing that astrobiology needs to be more careful about the difference between what it knows and what it assumes, that the field's working prior about life being common is not obviously justified by the evidence, and that treating it as justified leads to systematic overstatement of what specific findings mean. His position is not that life is rare, or that Enceladus is uninteresting. His position is that the uncertainty is real and large, and not being communicated honestly, and that the failure to communicate it honestly shapes how the field is perceived, how it is funded, and what questions it asks. His critique tends not to appear in the accounts of Enceladus that travel. The more carefully origin of life researchers examine the problem, the more specific the required conditions appear to be, not less specific. More early origin of life research from Oprin and Haldane in the 1920s through Miller and Urey in the 1950s tended toward a picture in which life arose from a warm soup of organic compounds with access to energy. The conditions seemed relatively permissive. What has happened since is that researchers have found the problem to be harder than the warm soup picture suggested. The specific molecules that life requires are not simply produced by mixing organic compounds in water and adding energy. They require specific reaction sequences, specific pH conditions, specific concentrations, specific protection from the hydrolysis that water itself causes, and in many cases specific mineral surfaces that catalyze the right reactions while inhibiting the wrong ones. The more the chemistry has been worked out, the more it has looked like a problem that requires not just the right ingredients, but the right environment in the right configuration at the right time. This does not mean life on Enceladus is impossible. It means that finding organic molecules and liquid water and an energy source is further from finding life than the building blocks framing suggests. The building blocks are necessary. They are not sufficient, and the gap between necessary and sufficient in the context of an unresolved origin of life problem is not a small gap. It is the entire question. There is an additional complication specific to Enceladus that the account does not adequately reckon with. Researcher Tara Jokic's work on the Pilbara Craton in Western Australia, some of the oldest preserved rock on Earth, has contributed to an ongoing debate about where life originated. Her findings support the argument made most prominently by David Deamer that dry-wet cycling occurring in shallow, subaerial hot springs at the surface may be a necessary step in the path from chemistry to biology. If Deamer is right, if the repeated drying and rehydrating of organic compounds is required for the formation of the first cell membranes, then a deep subsurface ocean on an icy moon is not just an imperfect analog for life's origin on Earth. It is missing a potentially necessary condition entirely. This debate is live in the literature. It has not been resolved. The hydrothermal vent model and the warm pond model are genuine competitors, and the Enceladus account has chosen the vent model because it fits the environment Cassini characterized, without acknowledging that the choice is contested. and that the contest matters for whether the habitability claim holds. There is a word that appears in almost every serious paper about Enceladus, and almost never surfaces in the accounts that travel from those papers, with its meaning intact. The word is habitable. In the technical literature, habitable means capable of supporting life as we know it. It does not mean life is present. It does not mean life is likely. It means the physical and chemical conditions fall within the range that known life can tolerate. A sterilized petri dish is habitable in this sense. Habitable is a necessary condition for life, not a sufficient one, and it says nothing about probability. It is a binary determination. The conditions are either within the range or outside it, and it is made by reference to the one example of life we have, which is Earth's. When the accepted account says Enceladus is potentially habitable, it is using the technical definition. When the listener hears potentially habitable, they hear something closer to might have life. Those are not the same statement. The first is about chemistry and physics. The second is about probability. The word performs the transition between them without announcing it. It arrives as a technical term and is received as a probabilistic one, and the account never stops to say that the transition happened. The habitability determination for Enceladus rests on 4 findings: liquid water, organic carbon, an energy source, and the chemical elements necessary for life as we know it. These 4 conditions are treated in the popular account as if they are equally well established. They are not. Liquid water first. The evidence for a global subsurface ocean on Enceladus is strong. The plume itself is the most direct evidence. Cassini's gravity measurements provided additional support. The libration data measurements of how Enceladus wobbles in its orbit, which depends on whether its interior is solid or liquid, supports a global ocean rather than a localized pocket of water. The evidence here is genuinely robust. The questions of how deep the ocean is, how well mixed, how long it has been liquid, and how long it will remain liquid are less settled, but the basic finding is solid. Organic carbon second. The detection is real. The IMS returned data showing carbon-bearing molecules in the plume, and the cosmic dust analyzer detected high-mass organic compounds in ice particles ejected from the South Pole. But the specific identities of those high-mass organics are still being worked out from the data the mass spectrometer readings require modeling to interpret, and different research groups have proposed different molecular identities for the same spectral features. The presence of organic carbon is established. The specific nature of that carbon, its abundance, its complexity, and its relationship to the ocean chemistry below are not fully resolved. An energy source third. The molecular hydrogen finding from 2017 implies that chemical reactions are occurring in the ocean that produce hydrogen, most likely through the serpentinization of rocks at the ocean floor. Serpentinization is a well-understood geochemical process in which water reacts with iron and magnesium-rich rocks to produce hydrogen and heat. It is the same process that drives the alkaline hydrothermal vents that Michael Russell's hypothesis invokes as life's cradle on Earth. On Earth, methanogens, microorganisms living in environments with no sunlight and no oxygen, use this hydrogen as their primary energy source. The conditions for this specific metabolism appear to exist on Enceladus. That is a real finding. But the conditions for a metabolism and the presence of that metabolism are different things, and the account has been sliding between them. The chemical elements fourth. Life as we know it requires carbon, hydrogen, oxygen, nitrogen, phosphorus, and sulfur, abbreviated NOPS. Carbon, hydrogen, and oxygen have been detected in the plume. Nitrogen has been detected as ammonia. Sulfur has been tentatively identified. Phosphorus has not been detected in the plume at all. Phosphorus is not a minor ingredient. It is the backbone of Dina and Rana, It is the central element in ATP, the molecule all known life uses to store and transfer energy. It is, in the assessment of many astrobiologists, a potential limiting nutrient, a factor that, if absent or scarce, would constrain or prevent the development of life, regardless of how favorable other conditions were. The non-detection of phosphorus is not proof of its absence in the ocean. Phosphorus compounds tend to be less volatile than the hydrogen and carbon dioxide that dominate the plume, and the plume may not be a representative sample of the ocean's full chemistry. A 2020 paper by Waite and colleagues modeled the likely phosphorus chemistry of Enceladus's ocean and concluded that phosphorus should be present, based on geochemical modeling of how rocks of the likely composition would dissolve in water of the measured pH. The modeling is careful and the conclusion is plausible. But it is a model output, not a measurement. Phosphorus in the Enceladus ocean remains an inference, not a detection. The account tends not to mention this. It presents all four habitability conditions as established, moves through them quickly, and arrives at the conclusion that Enceladus is potentially habitable without dwelling on the fact that one of the four central conditions has not been measured and is currently known only through geochemical inference. That is a gap, not a fatal gap. The modeling may be right, but it is a gap in the evidence that the building blocks framing has papered over, and papering it over has consequences for how the question is understood by the people whose support the next mission will require. The organic molecules Cassini detected in the plume are real, but organic molecules are not life. They are not even reliable indicators of life in an environment where the same molecules can be produced by hydrothermal chemistry, by the irradiation of simple carbon compounds, by non-biological processes that have been demonstrated in laboratory settings for decades. What Cassini could not do, and this is the gap that sits at the center of everything, is distinguish biological from abiotic organic chemistry. Cassini could not measure the chirality of the organic molecules in the plume, whether they were left-handed or right-handed. Life on Earth uses left-handed amino acids almost exclusively. A plume from a biotic ocean would be expected to show that asymmetry. A plume from an abiotic one would not. Cassini could not make that measurement. The IMS was not sensitive enough, and the flyby speeds were too high. Cassini could not measure the isotopic ratios of carbon and hydrogen in the organic molecules with the precision required to distinguish biotic from abiotic origins. Those ratios are among the most reliable biosignatures available in the geological record on Earth. They were essentially unresolvable in the Enceladus plume with the instruments available. Cassini could not determine the molecular weight distribution of the organic compounds in the plume with enough resolution to say whether the distribution looked biological, whether the pattern of which compounds were present in which concentrations followed the logic that life imposes on chemistry, or the logic that geochemistry imposes on it. These are not small gaps. They are the gaps that matter most. They are the measurements that would move the question from not ruled out to actually supported. They were not made. And the account built on what Cassini found has not, in most of its versions, stopped to name the shape of what Cassini did not find. There is something specific in the data that resists the fully abiotic explanation, and it deserves to be stated clearly, because this is not an inquiry that wants to argue in only one direction.
In 2021, a paper in Nature Astronomy by Regis Ferrier and colleagues modeled the methane production rates implied by the Cassini data and found that the concentration of methane in the plume was higher than what known abiotic hydrothermal processes could easily explain. The paper was careful. It explicitly considered multiple explanations, including the possibility that abiotic chemistry in Enceladus's ocean operates differently from what Earth-based models predict.
It did not claim to have found evidence of life. What it found was a residual, an anomaly, a number that the best available non-biological models underpredicted. Anomalies are not findings, but anomalies are where inquiry lives. The methane residual is not the building blocks of life. It is not evidence of life. It is a measurement that the best available non-biological models have difficulty reproducing, which means either the models are missing something, the measurement has an error, or something is producing the methane that those models do not account for. Biology would produce it. So would certain geochemical processes not well characterized in icy moon environments. The data does not distinguish between these possibilities. But the anomaly is real. The account that dismisses the Enceladus findings entirely makes the same error in reverse as the account that treats them as essentially confirmatory.
The anomaly deserves pressure. It is sitting in the methane numbers, underdetermined, waiting for instruments that do not exist yet. Those instruments, the ones that would actually move the question, are being designed. But the timeline is not what the account implies. The most developed mission concept for returning to Enceladus is the Orbilander, a concept study commissioned by NASA and delivered in 2021. Designed to both orbit Enceladus and land on its surface, carrying instruments capable of making the measurements Cassini could not.
The Orbilander concept includes something the account almost never pauses on, an instrument called a life detection mass spectrometer. A mass spectrometer designed specifically, not incidentally, not as a secondary capability, but as its primary purpose to look for the chemical signatures of biology. This instrument does not currently exist in flight-ready form. It is being developed. That fact alone is a statement about where the question stands. Cassini did not carry a life detection instrument. It carried a mass spectrometer designed for atmospheric and magnetospheric science that proved unexpectedly capable of detecting plume chemistry at a level of detail that generated 2 decades of scientific papers. The people designing the next mission responded by designing an instrument that would actually be built for the problem, and in doing so they drew a line clearly between what was found and what needs to be found. Building blocks of life is what you find with Cassini. Evidence of life is what you would need the Orbilander to find. Those are different instruments because they are different questions. The account has been treating them as the same question at different stages of resolution. They are not. The Orbilander, if approved, funded, built, launched, and successfully operated, would reach Enceladus in approximately the 2040s. If it is approved in the current planning cycle, which has not happened yet, it would be launched no earlier than the mid-2030s. The cruise to Saturn takes approximately 13 years. And then the science phase, and then the analysis, and then the papers. The question that Cassini opened in 2005 will not be answered before the middle of this century, at the earliest under the most optimistic assumptions. Most of the people who have dedicated their careers to this question will not be alive to see the answer. That fact belongs in the account. It is not in the account. The account presents the question as urgent and proximate as something nearly answered, only requiring confirmation. The actual timeline is generational. There is also a harder truth inside the Orbilander concept that the popular framing does not acknowledge. Even that mission, with its dedicated life detection instruments, its surface landing capability, its far greater sensitivity than anything Cassini carried, would not produce a definitive answer. A positive result would not be definitive, because distinguishing an independent origin of life from panspermia transfer requires capabilities beyond any current mission concept. A negative result would not be definitive, because if life exists but is sparse, which is what you would expect from a chemolithography-driven ocean far from any sunlight, the probability of detecting it in a surface sample of plume fallout is not certain even if the life is present. The Orbilander would constrain the question. It would characterize it more precisely. It might find something that transforms everything, but the gap between what the mission can do and what the account implies it will do is the same gap that has been running through this inquiry from the beginning. The Drake equation is usually introduced as a framework for estimating the number of communicating civilizations in the galaxy. It was not designed to be taken literally. Frank Drake wrote it on a blackboard in Green Bank, West Virginia in 1961 as an agenda for a meeting, a way of organizing what was not known into a series of questions that could in principle be addressed one by one as the science developed. It was a structured acknowledgement of ignorance. Drake himself was clear about this. The equation did not produce a number. It produced a list of uncertainties in a form that looked like a calculation. What happened to it afterward is instructive for everything about how Enceladus has been communicated. The equation traveled. It appeared in textbooks, in popular science writing, in Carl Sagan's Cosmos, in the opening arguments of SETI funding proposals. And as it traveled, the distinction between a structured acknowledgement of ignorance and an actual calculation began to collapse. The equation began to be used to produce numbers, those numbers reflecting the estimator's priors as much as any evidence. The Drake equation is the Enceladus account in miniature. The terms that matter most: the fraction of planets where life originates, the fraction where intelligence develops, are the terms most unknown. The values assigned to them in any given estimate reflect assumptions about how common life is that are derived from a sample size of 1. The equation cannot constrain those terms without a second example of life. It was always waiting for a second example. Enceladus was supposed to be where the second example might be found. The second example has not been found. And without it, the Drake equation remains what it was in 1961, a structured acknowledgement of ignorance that has been mistaken, repeatedly and persistently, for a method of producing answers. The public excitement about Enceladus is not really about Enceladus. It is about the Drake equation. It is about the fraction of habitable worlds where life actually arises, the term that, if it could be estimated from even one additional data point, would transform astrobiology from a field built on assumptions into a field built on evidence. Enceladus is exciting because it might provide that data point. Because if life is found there, the fraction goes from unknown to something not precisely known, but bounded, constrained, no longer purely a prior. The account has been feeding on that excitement for 20 years, presenting Cassini's findings as movement toward the data point the Drake equation needs. Cassini did not provide the data point. It provided conditions consistent with the data point being findable. Those are not the same thing. There is a specific incentive structure underlying why the gap between the papers and the account never closed. It is not corruption. It is not even necessarily a mistake. It is a structural feature of how science about potentially habitable worlds gets communicated, funded, and continued. A mission to Enceladus costs several $billion and takes decades from proposal to arrival. The case for that mission depends on public and institutional support. That support depends in part on the sense that what was already found is significant enough to justify the investment. And the phrase building blocks of life does more work for that case than the phrase conditions consistent with prebiotic chemistry. They are not the same phrase. They do not say the same thing. But one of them travels and one of them does not. This created a pressure that accumulated continuously in hundreds of press releases and news articles and documentary scripts and funding applications over the decade that followed the plume's discovery. It became the account. And now the account is what most people know about Enceladus, which means that what most people know is not exactly what Cassini found. It is what was decided to say about what Cassini found. There is a human cost inside that gap that does not appear in press releases or mission concept studies. It appears in the careers of scientists who have dedicated decades to a question that cannot yet be answered. working within a communication framework that requires them to overstate their findings in order to maintain the support their work requires. Knowing the difference between what they found and what they are saying they found, and living in that gap professionally every day. Sarah Seeger, who works primarily on exoplanet atmospheres, has spoken about this more openly than most about the experience of working at the edge of what current technology can detect, of knowing the instruments available are not quite sufficient, of publishing findings reported as closer to the answer than they actually are, and of living with the knowledge that the real answer is probably not coming within her career. That specific kind of sustained proximity to a question that cannot be answered, yet does something to the language science produces. It creates pressure toward the language of imminence. Always the next mission. Always the building blocks already found. Always the confirmation just requiring better instruments. And so the language of imminence accumulated. Each new paper from the Cassini archive added detail. Each new headline reported it as progress. The public impression was of a field making steady progress toward an answer. The actual situation was of a field doing everything it could, with a fixed dataset that is not sufficient to answer the central question, while waiting for a mission that may or may not be approved, on a timeline that extends past the career length of most of the people doing the work. The building blocks framing persisted not because the people using it were being cynical about the evidence. They were being optimistic about it. They were choosing the framing that matched their honest assessment of what the findings might mean, while knowing that the evidence did not yet justify that assessment. That is the gap between what you know and what you think is probably true given what you know. The gap between evidence and judgment. And every scientist navigates it continuously. The Enceladus account has been running in that gap for 20 years, not dishonestly, optimistically, with the genuine conviction of people who have looked carefully at a remarkable finding and concluded that it is pointing somewhere important, even though the instruments available cannot confirm the destination, and the journey will take longer than any of them will be alive to complete. The tiger stripes are about 130 kilometers long. Each one, 4 of them, roughly parallel, spaced about 35 kilometers apart, running across the south pole of Enceladus in a pattern that has no precise analog anywhere else in the solar system. They are not cracks in the way that word usually implies, not sharp, not clean, not the result of a single event. They are complex structures, bordered by ridges of ice pushed up by pressure from below, flanked by younger ice deposited by the plume fallout, surrounded by a region of surface that is warmer than the rest of the moon, by a margin Cassini's instruments detected clearly. The south pole of Enceladus, which should be the coldest part of a cold and dead moon, is the warmest region on its surface. The heat is coming from below. It is measurable. It is continuous. The tiger stripes have names: Baghdad sulcus, Cairo sulcus, Alexandria sulcus, Damascus sulcus, named after cities in the Arabian Nights following the AU convention for naming features on icy moons. Cities of story, applied to the fractures in the ice of a moon of Saturn from which an ocean is erupting into space. That naming choice embedded the tiger stripes, from the beginning, in a frame of imagination and narrative which turns out to be appropriate in a way the naming committee probably did not intend. Because the tiger stripes have become the site where the story the account wants to tell and the story the evidence actually supports have been quietly diverging for 20 years. The tiger stripes are where the plume comes from. They are the physical mechanism, the fractures through which pressurized water and gas from the subsurface ocean find their way to the surface. They are not metaphor, they are geology, but they have been described as windows into the ocean, as the mouth through which Enceladus speaks, as the place where the secret of the solar system is being slowly revealed. That metaphorical frame is doing the same work that building blocks of life does. It is organizing observations into a story that has a direction, moving towards something, in which the tiger stripes are thresholds where the hidden becomes visible. They are not thresholds in that sense. They are conduits. What that material contains is real and measurable. But what it means, whether it is evidence of life or evidence of chemistry, is not determined by looking through the tiger stripes more carefully. It is determined by having instruments capable of asking questions the tiger stripes cannot answer on their own. The total heat output from the south pole of Enceladus, estimated from Cassini's infrared measurements, is somewhere between 15 and 30 gigawatts. Even the lower end of that range is far more than the tidal heating models predicted when the mission was designed. The models predicted perhaps a fraction of a gigawatt from a moon of Enceladus's size and orbital configuration. The actual output is more than an order of magnitude larger. This discrepancy has not been resolved. The tidal heating models have been revised to try to accommodate the observed heat flow, but the revisions require assumptions about the interior structure of Enceladus, the rheology of its rocky core, the thickness and viscosity of its ice shell, the dissipation mechanisms operating in different layers that are not independently constrained. The models can be made to fit the observation by choosing the right parameters. But choosing parameters to fit an observation is not the same as understanding why the observation is what it is. The excess heat is one of the most important unresolved questions in the Enceladus dataset. It is also one of the least discussed in the popular account. Because the entire chain of reasoning that connects the tidal heating to the building blocks of life runs through the tiger stripes and the heat they are releasing. If the heat mechanism is not as well understood as the account implies, if the excess heat is still unexplained in ways that matter for the chemistry it drives, then the chain is weaker at its foundation than the account presents. Not broken. Weaker. And when you multiply uncertainties, when you ask what the probability is that all the links in the chain are correct, simultaneously the number that comes out is smaller than the number you get if you assess each link separately and find it reasonable. The account assesses each link separately. It does not do the multiplication. The multiplication is where the honest assessment of the conclusion lives. The snow on Enceladus is the purest water ice in the solar system. When the plume material falls back to the surface, the fraction that does not escape into Saturn's E-ring, pulled back by Enceladus's weak gravity, it settles as a fine, bright frost across the moon's surface. This is why Enceladus reflects nearly all the sunlight that reaches it. The albedo, the fraction of light reflected, is close to 1, almost perfect. The surface is continuously renewed by its own eruption, covered in fresh material from the ocean below, making it the brightest natural object in the solar system after the sun itself. A world that erases its own history as it writes it. A world whose surface is not a record of the past, but a product of the present. Not what happened, but what is happening, continuously in the ocean below, translated into snow and deposited on the surface, in a layer that grows and accumulates and reflects almost all the light that falls on it back into space. The plume is not just shooting water into space, it is coating the moon in itself. This is a fact about Enceladus that is genuinely strange in a way that does not require the life framing to be remarkable, and it points to something the account has not been honest about. What Cassini found, even stripped entirely of the building blocks framing, is a finding about the solar system that deserves the attention it has received. Small, cold, distant bodies can harbor liquid water driven by tidal heating that the early models said was too weak to produce it. The chemistry of the outer solar system is richer and more energetically active than anyone expected. The range of environments where interesting chemistry occurs is wider than the prior frameworks assumed. That is a real finding. It does not depend on life. It would be remarkable even if Enceladus's ocean turns out to be completely abiotic, even if the Orbilander arrives in the 2040s and finds nothing biological, even if the answer to the question of life, when it finally comes, is no. But the account has not been telling this story. It has been telling the other one, the one where the building blocks are found, and life is probably there, and the next mission will confirm what Cassini essentially showed. The chemistry story, which is the honest story, the one the evidence actually supports, has been subordinated to the life story, made to serve the life story, translated into the life story at the cost of its own accuracy. And here is the thing that is hardest to sit with honestly. The chemistry story and the life story are not fully separable. The reason Enceladus's chemistry is interesting, the reason anyone cares whether the organic molecules are complex, whether the hydrogen concentration implies active serpentinization, whether the methane is in excess of what abiotic models predict, is precisely because of the life question. The chemistry is interesting as chemistry, but it is urgently interesting, generation-defining interesting, worth billions of dollars interesting, because it might be pointing at life. Strip the life framing entirely, and the chemistry story loses the urgency that makes people willing to spend the decades it takes to build a mission to the outer solar system. The life framing is not just a distortion. It is also the reason anyone is looking. The excitement is real even if it has outrun the evidence. The building blocks of life is not just marketing language. It is the expression of a genuine hope that has been driving planetary science for decades, and that may, eventually, be vindicated by the very mission it helped make possible. Both of those things are true. They do not cancel each other out. They coexist in the account, unresolved. And the account does not acknowledge the coexistence. There is a photograph that does not exist, not a photograph that was taken and lost, or classified or never released. A photograph that could not be taken, that no instrument carried by any spacecraft has been capable of producing of the floor of Enceladus's ocean. Think about what that means. Every image of Enceladus that has ever been produced, every picture in every article, every documentary still, every NASA press release is a picture of the surface, the ice, the tiger stripes, the plume rising from the South Pole against the black of space. Every image is of the outside. The inside has never been seen. The floor where the hydrothermal vents are thought to exist, where the serpentinization is thought to be occurring, where the hydrogen is being produced, where the chemistry the account calls the building blocks of life is actually happening. That floor has never been photographed. It has never been directly measured. It has never been visited by anything. It is 600 million miles away and 30 kilometers below the surface, and it has been in total darkness for however long the ocean has existed, and no human instrument has ever touched it. This is the most important fact about the Enceladus account that the account never states directly. Everything, the building blocks, the habitability, the energy source, the organic molecules, the molecular hydrogen, the methane anomaly, the hydrothermal inference, the serpentinization model, the methanogen hypothesis, everything in the account is about a place that has never been seen. Everything is inference. Everything is model. Everything is the product of instruments that measured the shadow of the ocean, the material that escaped through 4 cracks in the ice, and then worked backward, through layers of modeling and assumption and interpretive framework, to a description of a place that no instrument has ever directly observed. The floor of Enceladus's ocean is the honest center of the account. Everything else, the plume, the organics, the hydrogen, is the periphery. The periphery is what has been measured. The center is what has not been seen. And the account has been built as if the center were as well characterized as the periphery. when the center is exactly as unknown as it has always been, which is completely, in the most literal sense. The framework that fills in the unseen floor is the framework derived from Earth, from mid-ocean ridges, from alkaline hydrothermal vents, from serpentinization as it occurs in the rocks of Earth's mantle under the conditions of Earth's ocean. The floor of Enceladus's ocean is being described in the language of a place on Earth that is not the same place, under conditions that are not identical, in a world that has been developing independently for 4 billion years. When a framework fills in what has not been seen, the framework's assumptions become the account's findings. And those assumptions, as this inquiry has traced them, are not settled. They are provisional. They are the best available prior, not a confirmed description of what is happening in the dark below 30 kilometers of ice. The building block of everything the account claims is the unseen floor. What would it actually mean to reach the floor? Not the plume, not the surface fallout, the ocean, a probe that melts through 30 kilometers of ice through material that is under enormous pressure, that refreezes as the probe passes, that would seal the hole behind any instrument that descended through it, and reaches the water below and measures it directly, in situ at the depth of the hydrothermal vents, with instruments capable of making the chiral, isotopic, and molecular measurements that the question requires. This is not a near-term concept. The technology for melting through 30 kilometers of ice does not exist. The communication system required to transmit data from a probe at that depth, through the ice to a spacecraft on the surface to Earth, does not exist. The power source required to sustain the probe for the duration of the mission does not exist in a form that could be miniaturized to fit through the borehole. The entire concept is beyond the current technological horizon in multiple simultaneous dimensions. And yet, it is where the question leads. Everything before it, the Cassini flybus, the Orbilander, the decades of analysis, is preparation. Characterization from a distance. Narrowing of the possibilities. The snow keeps falling on Enceladus. The tiger stripes keep erupting. The ocean below keeps doing whatever it is doing, producing hydrogen and organic molecules and methane in concentrations that the best abiotic models underpredict, in an environment consistent with the conditions for life, in a darkness that no instrument has yet penetrated. The account has been calling that darkness by a name that belongs to what might be in it, not to the darkness itself. The name is not wrong, exactly. The darkness is consistent with that name. But it is also consistent with other names, and the difference in how confidently those names are spoken is not a difference in evidence. It is a difference in hope. The hope is not nothing. The hope is why anyone is looking. The hope is why the instruments will eventually be built, and the mission will eventually be approved, and the spacecraft will eventually be launched, and the 30-year journey to the outer solar system will eventually end with a landing in the plume fallout zone of a moon that was supposed to be cold and dead, and turned out to be erupting. And what erupted was not just water. What erupted was a question that the prior models had not left room for. A question that arrived by accident through instruments not built to find it, on a mission designed for a different Enceladus entirely. A question about whether chemistry, given the right conditions and enough time, and the specific geometry of an icy moon in the gravitational grip of a gas giant, becomes something more than chemistry. That question was not created by the phrase building blocks of life. It was created by the plume being there when it was not supposed to be there, by the instruments returning data that did not fit the models, by the scientists who had to rebuild their interpretive frameworks in real time and reached for language that could carry what they were seeing to people who needed to understand why it mattered. The language they reached for was not wrong in its hope. It was premature in its confidence. And the distance between those two things, between a hope that is real and a confidence that the evidence does not yet support, is exactly the distance this inquiry has been pressing on. That distance is not a failure. It is the shape of the frontier. It is what genuine inquiry looks like from the inside, before the answer arrives, in the decades of careful work between the finding and the confirmation. It is uncomfortable to inhabit. It does not fit in a headline. It cannot be compressed into a phrase that travels. But it is where the science actually is, and where the science actually is pressed carefully, honestly, without the framing borrowed from a conclusion the instruments cannot yet confirm, is more interesting than the account that replaced it. A small moon in the outer solar system is shooting its ocean into space. The ocean contains chemistry that is genuinely remarkable and genuinely consistent with the conditions that, on one planet, preceded or accompanied the origin of life. The instruments that examined it were not built for the problem. The question they were asked to address is not resolved. The mission that might resolve it has not been approved. The people who have dedicated their careers to the question may not live to see the answer. And the plume keeps erupting. 600 million miles away, in the dark between Saturn and the stars, water and organic molecules and molecular hydrogen are being shot into space at close to 1,000 miles an hour, falling back as snow onto a surface that reflects nearly all the light that reaches it. A small world that was supposed to be cold and dead, erupting continuously, without pause, without awareness of being watched, without any relationship to the question of whether it is alone. The plume does not know it is evidence. It does not know it is being called a building block. It does not know that its chemistry has been translated into language borrowed from a conclusion that the instruments cannot yet confirm. It erupts because the physics requires it to erupt. Because the tidal pull of Saturn and Dione creates heat in the rocky core below the ocean, and the heat drives chemistry, and the chemistry produces gases, and the gases find the fractures in the ice and push through and become the plume that was not supposed to exist and was found by accident and changed the account of what the solar system is. The plume is not an answer, it is a pressure point. It is the exact shape of a question that the current instruments cannot resolve, asked by a world that did not intend to ask it, received by instruments that were not designed to hear it, translated into language that has done more work than the evidence supports, and sent back to a planet 600 million miles away. The tiger stripes stay warm in the cold. The snow settles on a surface that preserves it perfectly. The ocean below stays dark. And somewhere in that darkness, in a place that no instrument has ever reached, something is happening, chemical or biological, ancient or recent, solitary or abundant, alive or inert, that the account has been naming for 20 years with a confidence the evidence does not support, and a hope that the evidence does not rule out. The honest position is simpler and harder and more interesting than any of the names the account has chosen. It is this: something is happening in the dark below the ice, and we do not know what it is, and we have been looking at its shadow for 20 years, and calling the shadow by a name that belongs to what might be casting it, not to the shadow itself. The shadow is there. What casts it is still unknown. That is the finding, the only one the evidence actually supports. And it is enough. It has always been enough. It did not need the building blocks framing to be remarkable. It was remarkable before the framing, and it remains remarkable under the pressure that found the framing wanting. A small, cold, distant moon, erupting in the dark, casting a shadow that the instruments can almost but not quite read, waiting for instruments that do not yet exist, patient in the way that oceans are patient, which is to say entirely without patience or impatience, entirely without knowledge of being waited for, entirely itself, in the dark, in the cold, 600 million miles away, doing what the physics requires. The question is still open, the dark is still dark, the plume is still erupting, we are still watching. There is something that the account has never quite named about the waiting itself. Not the waiting for the mission, not the waiting for the instruments. The waiting that happens in the space between a discovery and its resolution, the specific texture of a scientific question that has been opened but cannot be closed, that sits in the literature accumulating papers that circle its edge without crossing it, that generates headlines every few years as new analysis extracts something from a fixed data set. Each extraction reported as progress toward an answer that the dataset was never capable of providing. That waiting is not passive. It is doing something to the question. It is shaping how the question is understood, who asks it, what language is available to ask it, and what kind of answer will be recognized as satisfying when it finally arrives. 20 years of waiting have not left the Enceladus question unchanged. They have sedimented assumptions into it. They have made certain framings feel natural, and others feel radical. They have created a community of researchers whose careers are structured around a specific version of the question, the building blocks version, the habitability version, the conditions for life version, and who will necessarily bring that version of the question to the instruments that eventually get built to address it. This matters in a way that is not obvious. The instruments that will fly on the Orbilander, if the Orbilander is approved, will be designed to look for specific signatures. Those signatures will be chosen based on the best current understanding of what life produces and what abiotic chemistry produces. That understanding has been developing for 20 years inside a field whose institutional framing has been organized around the building blocks account. The question of what counts as a biosignature, what signal, measured at what sensitivity, in what context, would constitute evidence of life rather than evidence of chemistry, is not a purely technical question. It is a question that carries the accumulated weight of 20 years of framings, assumptions, and institutional commitments. The instruments will be good. They will be the best instruments anyone has ever built for this problem, and they will be looking for the signatures that the building blocks account has taught the field to expect. What they might not be looking for is something the building blocks account did not anticipate. There is a concept in the philosophy of science called the theory-ladenness of observation. It means that what you see when you look at something depends on the theoretical framework you bring to the looking. Not because science is subjective, the world is not making itself up to match your expectations, but because observation is never raw, it is always organized. The human perceptual system and the instrumental systems built to extend it are not neutral recorders of what is there. They are filters shaped by prior commitments about what is worth recording and how. Thomas Kuhn wrote about this in the context of scientific revolutions. What he noticed was that the history of science is not a smooth accumulation of correct observations building toward a complete picture. It is punctuated by moments when the framework that organized observation broke down, when anomalies accumulated beyond the framework's ability to absorb them, and a new framework emerged that reorganized everything. What counted as observation changed. What counted as evidence changed. Findings that had been invisible in the old framework became central in the new one. Findings that had seemed definitive in the old framework became puzzling or irrelevant. Kuhn's account is contested in various ways. The philosophy of science has moved significantly since the 1960s, and the strong version of his argument is not universally accepted. But the basic insight that what you find depends in part on what you are equipped to find is not controversial. It is a working assumption of good experimental design. You have to build instruments for the signal you expect. You have to calibrate for the range you anticipate. You have to design the analysis pipeline for the question you are asking. And if the signal is not the one you expected, if the range is not the one you anticipated, if the question the data is actually answering is not the question you designed the analysis for, the finding may not register at all. Or it may register as noise. Or it may register as an anomaly that gets filed as interesting and not pursued. The Enceladus account has been organized around a specific signal. The signal is evidence of conditions for life as we know it. That is what the instruments were retasked to look for after the plume was discovered. That is what the analysis pipelines were designed to characterize. And they found it in the sense that the conditions appear to be present. But the question of whether that signal is the right signal for the actual state of the ocean is one the account has not examined. Consider what it would mean if life in Enceladus's ocean, if it exists, is not organized around the biochemistry that Earth life uses. Not a radically alien biology in the science fiction sense. Something more subtle. A chemistry that uses the same basic elements but has arrived at different solutions to the same problems. Different amino acid chirality. Different nucleotide structures. Different membrane chemistry. Nothing that would look wildly foreign necessarily, but different enough that the specific biosignatures the Orbilander's instruments are being designed to detect, the ones derived from Earth biochemistry, from what methanogens produce, from what left-handed amino acids look like in a mass spectrometer, would not register as clearly as expected, or would register differently, or would be present alongside abiotic signatures in ratios that the analysis pipeline interprets as ambiguous rather than positive. This is not a scenario the account discusses. It is not even a scenario that most of the mission design literature examines in depth. The instruments are being built around the assumption that life, if present, is similar enough to Earth life that Earth-derived biosignatures will be detectable. That assumption may be correct. It is probably the right working assumption given that we have no other template. But an assumption built into the instrument design is not just a methodological choice. It is a constraint on what the mission can find. If the assumption is wrong, the mission may return data that the analysis pipeline cannot correctly interpret, not because the instruments failed, but because they were looking for the wrong signature of the right phenomenon. This is the deepest version of the theory-ladenness problem as it applies to Enceladus. The building blocks account has defined what counts as a finding. It has defined it in terms of Earth biochemistry, and the mission being designed to follow it up is inheriting that definition in hardware. There is a scientist whose name appears almost nowhere in the popular Enceladus account, but whose work sits at the conceptual foundation of every serious argument about what life detection in an ocean world actually requires. His name is Lee Cronin, and he works at the University of Glasgow on something he calls assembly theory. The details of assembly theory are technically demanding, and its reception in the scientific community is genuinely mixed. Some researchers find it a powerful new framework for thinking about complexity and life. Others find the formalism problematic. But the core idea is one that the Enceladus account urgently needs to reckon with, regardless of whether assembly theory in its specific mathematical form survives critical scrutiny. The core idea is this: life is distinguishable from non-life, not by the presence of specific molecules, but by the complexity of the molecular ensemble, by the degree to which the molecules present could only have been assembled by a process with memory, with selection, with the kind of causal structure that biology imposes on chemistry. A single amino acid can be produced abiotically. A specific protein, built from a specific sequence of amino acids that performs a specific function, cannot, not because the chemistry is impossible, but because the probability of it assembling without the guidance of a replicating evolving system is essentially zero. The molecule carries in its structure the history of the process that built it. Cronin's argument is that this distinction between the complexity achievable by undirected chemistry and the complexity achievable only by directed, selective, iterative processes can in principle be measured, not by identifying specific molecules as biological, but by characterizing the overall assembly index of the molecular mixture. Life doesn't just produce complex molecules. It produces a specific kind of complexity, a kind that exceeds what undirected chemistry generates by orders of magnitude, and that is detectable in the distribution of molecular structures even without identifying any single molecule as a biosignature. If this is right, and it remains genuinely debated, it changes what you look for in a plume sample. You look not for specific chiral signatures or isotopic ratios, but for the statistical fingerprint of directed assembly in the molecular ensemble as a whole. This is a different measurement. It requires different instruments, different analysis methods, different definitions of what a positive result looks like. It is not what the current Orbilander concept is primarily designed to find. Whether assembly theory in its current form survives is not the point. The point is that the conceptual space of what life detection might mean is larger than the building blocks account has assumed, and that the 20 years of framing the question in terms of building blocks has narrowed the field's instrumental imagination in ways that have real consequences for what the next mission will be capable of finding. The account chose a specific answer to the question, what does life look like from the outside, and built the follow-up mission around that answer, before the question had been fully worked out. Now press on the ocean itself in a way the account has not. The ocean of Enceladus, if it is as large as the current models suggest, contains a volume of liquid water comparable to Earth's oceans. That is an enormous volume, and it has been to the extent that the tidal heating models are correct. Liquid for a very long time, possibly billions of years. In that time, if the chemistry is as active as the plume suggests, an enormous amount of chemical processing has occurred. Molecules have been synthesized, broken down, recombined. Energy has flowed through the system. The specific chemistry of the ocean today is the product of billions of years of that processing. On Earth, 4 billion years of chemistry produced life, and then life transformed the chemistry so thoroughly that the pre-biological chemistry is almost unrecognizable in the geological record. The atmosphere changed, the ocean chemistry changed, the rock record changed. Life did not just inhabit the chemistry, it rewrote it. If life exists in Enceladus's ocean and has existed for a comparable timescale, it has had billions of years to rewrite the ocean's chemistry. The ocean we would find if the Orbilander ever descends through the ice, if the technology for ice penetration is ever developed, if anything ever reaches the floor, would not be a pristine pre-biological environment, it would be a biosphere. Billions of years old, as transformed by its own biology as Earth's ocean is by ours. And if life does not exist and has never existed there, the ocean we would find is a 4 billion year archive of abiotic chemistry, running in the dark under pressure. That is also extraordinary. That is also something no instrument has ever characterized directly. That ocean, whether biotic or abiotic, is one of the most information-rich environments in the solar system. It has been running an experiment that started at the same time as Earth's chemistry and has been running continuously, in isolation, without interruption, without the catastrophic resets of impact events that periodically sterilized or transformed early Earth's surface environments. The plume is a tiny sample of that experiment. A sample drawn from the most active, most geologically dynamic region of the ocean, filtered through the ice, dispersed into space, collected by instruments flying through at 8 kilometers per second. What the experiment has been producing for 4 billion years is not knowable from that sample. The plume is to the ocean what a single sentence is to a library: real, meaningful, containing information that the larger work also contains, but not a substitute for the larger work, and not a reliable guide to everything the larger work contains. The account has been treating the sentence as if it were the library, not because anyone decided to, because the sentence was what was available, and the library is 30 kilometers below the surface and unreachable, and science works with what it has. But science is also supposed to be honest about what it has. And being honest about having a sentence when the question requires a library is not the same as having given up on finding the library. It is knowing where you are. There is a version of the Enceladus story that has not been told yet, because the evidence for it does not exist yet, but whose outline is visible in the shape of everything the account has not been able to resolve. It is the version in which the ocean is abiotic, in which the 4-billion-year chemistry experiment has been running in the dark without ever crossing the line from chemistry to biology, in which the methane anomaly is explained by a geochemical process that the current models have not yet characterized, in which the organic molecules are real and complex, and produced entirely by hydrothermal chemistry and serpentinization, without any biological contribution, in which the conditions for life, as defined by the Earth-derived framework, are genuinely present, and life has genuinely not arisen. That version is consistent with everything Cassini found. It is not the account's preferred version, but it may be the true one. And if it is, it carries implications that the account has never examined, implications that are in some ways more interesting than the implications of the version the account has chosen. If Enceladus's ocean is abiotic after 4 billion years of favorable conditions, the question it raises is not whether we are alone. The question it raises is how rare the transition from chemistry to biology actually is. Not how rare the conditions are. Enceladus would be demonstrating that the conditions can exist far from the sun, in small icy moons with no surface, no sunlight, no dry-wet cycling, in environments the early models said were too cold and too dead to be relevant. The conditions the abiotic Enceladus would show are not rare. The transition itself, the specific event or sequence of events that turns chemistry into something that replicates and evolves, might be. That is a profoundly important finding. It does not get the headline. It does not generate the documentary. It does not land in the Drake equation as a reduction of uncertainty in the direction of life being common. But it is real information about the universe. It is the kind of information that transforms a prior rather than confirming it. It is the kind of finding that makes the question harder and more interesting simultaneously. The account has been built around the hope of finding life. It has not been built around the possibility of finding something that explains why life has not arisen, and what that would mean, and why that finding would be as significant as finding life in a different way. Not more significant, as significant. A second data point showing that the conditions for life can exist for billions of years without producing it is as informative about the origin of life problem as a second data point showing that life arose independently. Both answers constrain the question. One of them does not get press releases. There is something else the account has not examined that lives in a completely different part of the problem. It is the question of time, not the age of the ocean, which has been discussed in the context of how long life would have had to arise, but the time of the observer, the specific moment in the history of the solar system at which the inquiry is being conducted. Enceladus has been erupting, by the best current estimates, for millions to billions of years. The tiger stripes may have been active in something like their current form for hundreds of millions of years. The ocean below has been liquid by the tidal heating models for a timescale that is genuinely geological, and the inquiry into what the plume means has been underway for 20 years. 20 years against hundreds of millions. The sample is not just spatially limited, drawn from the tiger stripes rather than the whole ocean, from the plume rather than the floor. It is also temporally limited in a way the account does not discuss. The chemistry that Cassini measured is the chemistry of the plume right now, in the specific orbital configuration of the current epoch, at the specific level of tidal heating that Saturn and Dione are currently producing. That chemistry may not be representative of the ocean's history. It may not be representative of the ocean's future. If the tidal heating varies over geological timescales, and the models suggest it does, as orbital resonances evolve and the internal structure of the Moon responds to the heat it is generating, then the chemistry of the plume varies too. The concentrations of hydrogen, the organic content, the temperature of the water at the hydrothermal vents, all of these are functions of the heating rate. The ocean Cassini sampled is a snapshot of a dynamic system taken at one moment in its geological history. Whether that moment is representative of the ocean's long-term state, whether the conditions favorable for life as characterized by the current measurements have persisted for long enough for life to have originated, is not knowable from the snapshot. This is a form of temporal underdetermination that sits alongside the chemical underdetermination already examined. The data cannot tell us what the ocean was like 10 million years ago, or 100 million years ago, or at the specific moment if there was one when the conditions for the origin of life were most favorable. The snapshot might be showing us the ocean at its best moment for life, or at a moment that is actually less favorable than the historical average, or at a moment of unusual activity that will subside in another few million years, and leave the ocean far less chemically active than what Cassini measured. The account presents the current state of the ocean as the relevant state.
But the origin of life is not a current state problem. It is a historical problem. It depends on what the conditions were at the time the transition from chemistry to biology either occurred or failed to occur. And the current state is the only state the data can show. What all of this adds up to the theory-ladenness of the instrument design, the assembly theory problem, the 4 billion-year chemistry archive, the abiotic Enceladus possibility. The temporal limitation of the snapshot is not a case against the Enceladus inquiry.
It is a case for understanding the inquiry more honestly than the account has allowed. The Enceladus inquiry is one of the most important scientific endeavors currently being planned. The questions it is trying to address: whether life exists elsewhere in the solar system, what conditions favor the origin of life, how common habitable environments are in the outer solar system, are questions that matter in ways that extend far beyond the scientific community. They are questions about what the universe is, about whether the chemistry that produced us is a quirk of one warm, wet planet, or a feature of a universe that tends under the right conditions toward complexity, toward self-organization, toward something that experiences itself. Those questions deserve the honest account. Not because the honest account is less exciting, it is, if anything, more exciting, because it places the inquiry at the actual frontier rather than just beyond the last finding. Not because the honest account is more fundable or more sustainable or better at generating public support, it probably is not, in the short run, but because the inquiry is too important to be built on language that has outrun the evidence. The building blocks are probably there. The conditions are probably favorable in the technical sense. The methane anomaly is real and unexplained, and may be pointing at something that transforms everything. The plume is extraordinary regardless of what it contains. The ocean below is one of the most interesting environments in the solar system, regardless of whether anything living has ever touched it. None of that required the overstatement. None of it requires the conclusion to be imported before the evidence arrives. The snow on Enceladus does not know it is remarkable. The tiger stripes do not know they are being watched. The ocean below does not know it is the subject of the most important unanswered question in planetary science. It runs its chemistry in the dark because the physics requires it to, on its own timescale, in its own way, indifferent to the frameworks being built 600 million miles away to describe what it is doing. And somewhere in the gap between the chemistry the plume shows and the answer the question demands, between the instruments that were not built for this and the instruments that do not yet exist, between the account that has been running for 20 years and the honest edge of what the evidence supports, somewhere in that gap, the actual inquiry lives. It is a harder place to stand than the account suggests. It offers less certainty, less proximity to the answer, less of the satisfaction that comes from a question that sounds nearly resolved. But it is the real place, the place where the finding actually is, the place from which the next 20 years of work will have to depart if it is going to reach something true. The dark below the ice is not waiting to be confirmed. It is waiting to be reached. That is a different kind of waiting. It requires different instruments, different patience, different honesty about the distance between here and the answer. The plume is still erupting. The question is still open. The distance is real.